you have to be able to read a topographic map to be able to answer a couple of the questions actually on the CDA. You guys, I believe it's odds tomorrow, so you should be taking yours tomorrow. Let's see, let me pull up the right thingy and unfreeze it. This is technically the last day of the 6 weeks, so this is the pull day for grades. You needed to have everything submitted by midnight, probably in all of your classes, for us to be able to grade things and then get them switched over from Canvas to Parent Portal so they can pull stuff digitally in the morning. So there's no opener today. I do have a paper copy of the review if that's what you need. I'm pretty sure I did this in order, question by question. It's not like the exact questions that are on the test or the CDA, but it is pretty gosh darn close. It's the same material. This has been a while, and we covered a whole bunch in the 6 weeks. So the first one, let me grab a review so I know what the question says. I was delirious trying to get this one together. This is one of the last things I did over the break. It says, how do we know the makeup of the structure of the interior of the Earth? All right, we know that it goes, obviously the crust is solid. That's what we walk on. But then we go to through the asthenosphere, we go into that plastic, which is a very, very slowly moving solid, that plastic upper mantle, okay? And then as we transfer to the outer core, it's liquid. And then as we go to the inner core, it goes back to a solid. And the way that we know that is because we have seismographs. Okay, so there's two major types of seismic waves that go through the interior of the Earth, not the surface waves, not the earthquake ones, but the ones that actually penetrate into the Earth. You have P waves, your primary wave. This would be the first wave to arrive somewhere else on the planet as it's traveling through the Earth. P waves are always faster than S waves, always. And they can go through both solids and liquid. Now, when they change their medium, when it changes the density, it sort of bends the wave. We call that refraction. It's like if you go fishing, that fish is not where it looks to be because the light changes speed as it travels from a gas to a liquid. This isn't a gas to a liquid. This is a solid to a liquid back to a solid. P waves, because they can go through both, they can actually come out on the other side of the Earth. I didn't put up the big structure, and you can go back into your notes and look at it if you want to. It's not on the test. But as waves travel through the Earth, we have two shadow zones because of the way that P waves refract, but they can still go all the way out on the other side of the Earth. S waves can't do that. S waves can only travel through the solid, so they can travel through the crust and they can travel through the mantle, but they can't travel through the outer core, which is they can't go through the outer core, they can't go into the inner core. So there's like a huge section on the other side of the Earth that you won't see an S wave, but there's only two small sections that you won't see a P wave on the other side. And that's how we know not only the fact that it goes solid, liquid, back to solid, but we also know how thick those layers are because of the refraction of those P waves. So there's a few things on here. This is actually the first two, if I'm not mistaken. Knowing the makeup of the structure of the interior of the Earth, and also the differences between the two major types of waves. P is primary, they arrive first. S is secondary. I didn't make you calculate the speed and how much time would occur between the two waves. I didn't go that far into this. I could have, but we just didn't go there. I've been cutting out most of the mathematics in this class, and it's been almost completely conceptual. So once again, this is the first couple. We didn't understand the makeup of the interior of the Earth until we had these seismographs, which were the 40s, if I'm not mistaken, somewhere around there. We just didn't have the technology. It's not that we were stupid. We just didn't have a way to measure it. All right, you have to be able to read a topographical map. Been a long time. Okay, so this map, we have a couple different questions on here, and I don't know if I answered them in the right order up on the thing. First one says, which way is Deer River flowing? Okay, so Deer River is this one right here. Okay, these V's, how you see how they're pointing from the way that it's coming from. So Deer River is actually going from the north to the south. It is flowing south, whereas Bird Creek, the one that's next to it, I have a feeling that that's Deer River is coming from the north. It originates from the north. It flows south. Just depends on how I'm going to ask the question. Once again, these V's, they show the direction it's coming from. So Bird Creek, they can't see me pointing. It's one of the reasons why I got this one. These V's are pointing to the right, which is east. So Bird Creek is originating from the east, but it's actually flowing west. And then when it joins back up with Deer River, then they both end up going south and they empty out into what's called Wolf Pond on here. I can't remember which way I asked the question on the test, but you need to know from the lines on the map. And I'm not going to like put north down. It's up is north, right is east, left is just normal cardinal directions. I'm not going to try to trick you. You have a couple of questions reading the topographical map. Once again, the arrow points the direction it's coming from, not the direction that the water's flowing. I also could have asked you to have calculated the speed of the river knowing the gradient. We didn't do that. Just didn't get that far into this. Contour interval. So you're going to find these dark lines. Like this is 50. This is 100. There's normally 1, 2, 3, 4, 5. And the difference between 50 and 100 is 50. There's 5 lines, 50 divided by 5. And this is in meters. I know it's in meters because that says kilometers, not miles. When you take the total difference between the two dark lines, the interval lines, and divide it by the amount of contour lines in between them, 50 divided by 5, the interval of this map is 10 meters. I'm pretty sure you have to be able to do that one too. And then let's see, the last one that's on here, I think that's all of it. The other part I think that I put on here, Wolf Pond, G, this is the shore of this pond. If the interval is 10, and now we're going down in elevation, it would be 50, 40, 30. If you were at the ocean, you wouldn't even have to calculate anything because the ocean is at sea level, which is 0. It's been a very long time since we've done these, and I know you have at least 2 questions. The CBA is 20 questions long. Are there any questions on reading this? It's just been a while. Right. I didn't check my online attendance. I'll do that here in just a second. What happens at the edges of tectonic plates? That's where all the fun stuff happens. That's where the Earth is going crazy, where you have subduction. If you've got oceanic and continental, the oceanic is always more dense. It's going to go underneath the continental. This is where we see all the geographical activity, primarily volcanic activity. Yes, earthquakes can happen there. Tsunamis can happen when you have oceanic. They're constantly moving because of, pause it here so I can check online. They're constantly moving because of the convection currents that push the asthenosphere, push those plates. Pen. Where's my pen? Where's my pen? Oh, it's over there. But like I said, the big thing that happens at the edges of these plates, particularly oceanic and continental, is you have lots of volcanic activity. Let's see. I see Braylon, Chase, Erica, and Chase, Erica, Joseph, Sarah, and here, Alex, Otis. I don't see Caitlin yet. Isai, Taylor, Kale, Cameron, Dylan, Jimmy. Let me see who is not here. I don't see Colton. Okay, let me put this back on here. Sorry. I'll check attendance again. I just shocked myself twice. How do you shock your own hand? Okay, that was weird. That was really weird. So this is what causes the motion of tectonic plates and what happens at the edges. Yes, you can have oceanic trenches. You can have possibly mountains that are being built if you have continental. It just depends on, if it's up here on the review, I'm going to ask you a question in some way, shape, or form. What type of boundaries are coming together? Anybody still need that one? Next question that I have on here. What is so unique about the island/country of Iceland? We even watched a documentary on this. Iceland is a pure volcanic island. Okay, it is sitting on top of a hotspot. There are other hotspots on our planet. Hawaiian Islands are a hotspot. Yellowstone's a hotspot. The Galapagos Islands are a hotspot. Canary Islands are, there's tons of them. It's not like Iceland's the only one. The thing that's really different about Iceland is that its hotspots trapped within the Mid-Atlantic Ridge. Most volcanic islands that are caused by a hotspot, the hotspot doesn't move. The crust moves over the top of the hotspot. And so you get a chain of islands like the Hawaiian Islands. And with the Hawaiian Islands, they're moving, the plate's moving essentially west. So the plates that are further to the west, like Kauai, which I don't know all the island names, I don't, but Kauai is further to the left. It's one of the smaller ones. It's where they filmed Jurassic Park, actually. That's older. But the main Hawaiian island, the big one, which is the tourist trap that you really don't want to go visit, just for your information, that one's the younger one. They all have volcanic activity. It's just the plate is moving over top the hotspot. Iceland is a little different. It's trapped. It's literally trapped in the ridge. The ridge is not moving. The ridge is pushing the plates apart. So Iceland didn't go anywhere. It's just going to get bigger. How has Earth's history been recorded on the ocean floor? Pretty sure this is the next one. In a ridge, such as the Mid-Atlantic Ridge, it's the most important one because it ripped apart Pangea. So just like when you have a scab and you move the wrong way and it tears and you start to bleed, except it's not bleed, it's lava. This thing tears and up comes that magma, which has lots of iron in it. Iron responds to magnetic fields. The iron within the magma aligns with magnetic north and south. It can't help it. Iron is one of the 3 magnetic metals. There's only 3, iron, nickel, and cobalt. When that magma, which is lava at this point, cools and turns to igneous bedrock, because it's igneous inside of the earth, the iron gets frozen in place. It gets trapped. Okay, so fast forward about 40,000 years, give or take, and we have the next reversal. Actually, it's a little longer than that, but it doesn't matter. You have a new tear. The poles have flipped. Well, iron, once again, can't help itself. It's still going to align with north and south, which is now opposite direction. It cools. It gets frozen in place. You have another magnetic reversal. Same thing happens, and you have alternating reversals of the poles that are literally frozen in that igneous basalt, in that bedrock forever. It's called magnetic striping. It can happen in other places besides the bottom of the ocean. I personally have been down in the bottom, well, not the very bottom, but as low as they'll let you go in Carlsbad Cavern, and the iron is reversed down there in the dirt. But most of it's going to be recorded. I really wish I would have known what they were telling me, because I would have taken some of the dirt. I would have brought it, but I didn't know that's what it was. Probably would have gotten in trouble if I would have done that. But it would be cool to have some that had a reversed polarity. All right, the ice ages. Ice ages sort of amplify evolutionary advances. The Huronian one, okay, the oldest one that we have record of from about 2.5 billion years ago, that's the one that, it's not the only reason why it happened, but it triggered photosynthesis in cyanobacteria. Most of the environment, the air that was present before that cyanide bacteria would kill us if we breathe, like 2 breaths kind of kill us. That bacteria pumped oxygen into the atmosphere. Extremely important evolutionary milestone. I know it's just bacteria, but it's that photosynthetic change. You fast forward a whole bunch of time, and now we're at the end of the Precambrian, and we're going into the Cambrian. And the next one, the Cryogenian, we call this snowball Earth. There were 4 glaciations that happened with this one. This is the one that triggered the advancement of complex multicellular life. Things like prokaryotes, euglena, amoeba, volvox, diatoms. You should have known those words from biology. I just don't know what they teach in biology here. But this was over a rather long period of time. That was the one that triggered complexity. And at the end of Snowball Earth, that's what triggered exoskeletal development. I didn't put the specific years on here because it was a nice span of time. All right. What's the next one say? How do we know that Antarctica was once much warmer and closer to the equator? Okay. Antarctica and Siberia have ginormous coal beds. Coal beds formed from like tropical kind of swampy vegetation. That's not happening in Siberia and Antarctica right now because they're frozen. So these two areas, which one is at the very towards the North Pole, and the other one's at the South Pole, literally at the South Pole. They had to have been closer to the equator at one point in time in order to support that swamp-like habitat. Specifically in Antarctica, there are fossilized Glossopteris ferns. That was one of the big changes in the Devonian, were those seeded ferns. The coal beds in Siberia, when we had the rifting that happened with Pangea, that's one of the reasons why the Siberian traps went just crazy. That volcanic activity that was shooting magma, well, lava at that time, like a mile into the air and triggered the Permian extinction. It was feeding off of those coal beds. And there's other things like fossilized organisms that are present in both places. When Pangea came together over 400 million years ago, it rose, or raised, I guess, the Appalachian chain on the East Coast. And that's the Urals over in Germany. That's the other side of it. This actually triggered an extinction event because of glaciation. You didn't have any ice whatsoever in the Triassic, when Pangea first came together. As it was coming together, before it was completely solidified, you did have a glaciation. All right. What specific Cambrian species survived many extinctions only to become extinct in the Permian Triassic extinction? All right, the biggest of the extinctions was the Permian Triassic. This was the one that was started by the Siberian traps exploding. We had glaciations that were going back and forth. We had acid rain. Man, the copier made horrible copies. Wiped out 96% of the marine life. That wasn't so bad for the terrestrial, especially the plants. They had vascular tissue. They were pulling up water from their root system that was filtered by the earth. The marine life took such a big hit because the oceans were poisonous. They were toxic, very, very low levels of oxygen, very high levels of heavy metals, things like lead and mercury, which are toxic to us. Don't chew on something that has lead paint on it. The organisms that were stuck, we call that being sessile. You can't swim, you can't move, you can't crawl away. Those were the ones that primarily died out. The poor trilobites were completely and totally destroyed. The trilobites survived the Ordovician extinction, the Devonian Silurian extinction. They kept surviving and surviving and surviving, but they could not survive this one. Even though most of them could move, well, they all could move. Some of them were hunters, they were predators. The ocean was just too toxic. Let's see here. What's the next one on here? There are two major causes of abrupt extinction. What are they? Most extinctions have some type of volcanic activity, but that takes a long time. It can cause nuclear winter, it can cause acid rain, it can cause ocean anoxia, but it's not instant. It takes time. The sudden extinctions are caused by some type of extraterrestrial impact. I really should have three things up here. Asteroids, which is the one that took out the dinosaurs. Meteors, which are smaller than asteroids. Asteroids are the largest, but also comets. I really should have said three things. But it's extraterrestrial impact, not aliens, just things that are falling from the sky. But if this wouldn't have happened, then we wouldn't have had the advances. Extinctions knock out your top everything, and they allow the little guys to squeak through. They allow the things that are still evolving to be able to take over, which was good for us that the asteroid slammed into the Earth 65 million years ago, because our ancestor, that little shrew thing, which will, next week, I'll tell you the name of that particular little rat-looking thing. Little, like literally like rat, is what all mammals came from. Got one more here. All right, so what was the age of the fish? Even though we had one that started in the Cambrian, almost every type of ancestor of fish evolved in the Devonian. They didn't all make it through the extinctions, but the bony fish and the lobed fish and the rayed fish, like sharks, they all started in the Devonian. Some made it through, some didn't. The Silurian, the only one I really didn't put up here because it's not on the test, the Ordovician was the evolution of vertebrates. The Devonian was the evolution of the fish, except for that one. You also had the very earliest of amphibians starting in the Devonian. The Silurian saw the motion of things onto land. So amphibians onto land, insects onto land, plants onto land. The plants were still in early stages. They didn't have seeds. They had spores. They didn't have vascular tissue. They had to be either in or right next to their water source. The insects, feeding off of the spores, triggered the seed coat. So we had seeded ferns that did not have vascular tissue first. And then eventually we had gymnosperms, which had both. And the gymnosperms were the ones that went much further in the land. That allowed the reptiles to start to come out in the Carboniferous, specifically the Pennsylvanian, but I didn't split the Carboniferous apart into the Mississippian and the Pennsylvanian here. The Carboniferous did see the advent of vascular tissue, saw the advent of the seed coat. Once again, this was triggered by the insects. Plants moved further inland. This was when the first reptiles, the captorhinomorphs, things that look like little green anoles, little green lizards. That was the beginning of the push of the reptiles onto land. The reptiles went further into land than the amphibians because they had that hard shell on their egg. They had the amniotic egg. The amphibians didn't. They still have to lay, they still do now. They have to lay their eggs in water or they'll dry out. The Permian is the age of the reptiles. This is where we also saw the first of the mammal-like therapsids, which one specific species made it through the Permian extinction. That was the granddaddy of all mammals, but it was still a half reptile, half mammal type organism. We'll talk more about those guys. I can't remember what day it is. It's next week when we go into the Mesozoic. At the end of the Permian, when Pangea started rifting apart, you had the Siberian traps that were going crazy for over 1 million years. Actually, it was about 2 million years, but full capacity for 1 million years. Snowball affected a whole bunch of things, not necessarily snow, but acid rain and just toxic fumes. That was the beginning trigger. Yes, there was an asteroid impacted with all of this as well. Let me check my email in just a second. This was the largest extinction of record, where at least 90% of marine life, about 75 to 76% of your terrestrial life went out too. Because then the plants actually weren't hurt that bad. The Permian extinction allowed for the rise of the dinosaurs. And right now it looks like I'm going to have 2 different lessons on dinosaurs. One about their evolution and the other about specific ones. The Cretaceous, the end of the age of the dinosaurs, when Baptista slammed into the Gulf of Mexico off the Yucatan Peninsula, that is what allowed for the rise of the mammals. Mammals and dinosaurs, if you're talking about therapsids, no, they were evolving at the same time. The mammals were just really, really small because the dinosaurs would eat them. So they became nocturnal, they hibernated, and they tend to go underground. Otherwise, the dinosaurs would jump on them and eat them, and then they would die. Most therapsids were actually taken out by dinosaurs. It was that one that really made it through. And then after the Cretaceous extinction, its great billion times grandbaby, that little rat thing, made it through and somehow turned into us over 60 something million years. Our species has only been around for about 2 million years if you count all the hominids. I haven't done the Cenozoic notes yet, but I know I will have a section about human evolution in there too. That will be probably after spring break. I do not think there's another slide. That should have been everything. Is there anything that you did not get on this review? Because this is what you need to be able to do for your test. Right? Let me pause this. Stop this. And I need to see if there's anybody in here that sent a notebook